Yeah, good afternoon, everybody. And our next speaker, Siddharth Barman. He is currently associate professor at IISc, and he is also Mindtree chair in the Department of Computer Science and Automation. There, before joining IISc, he was postdoc at Caltech, PhD in computer science from University of Wisconsin Madison. Siddharth is recipient of ACM India Early Career Research Award 2023, Young Engineering Award by Indian National Academy of Engineering INAE. He is also an associate of ISSC, Indian Academy of Sciences. His research lies at the interface of computer science and microeconomics, especially algorithmic game theory and fair division. Siddharth, please.
Great, thank you. Thanks for the introduction. Let me thank the aRtCS teams, in particular Shweta, for the invitation. Very delighted to be here at the inauguration of the center that promises to be both a catalyst and a glue for the growing theory community in the country. So extremely happy, and again, thank you for all of you. It's a Saturday evening, and I'm very happy to see such a almost a full class. So I'll talk about two complementary research themes, and the big purpose of my talk is to share some of the passion, some like the excitement I have for these two research themes, and I will give you a big picture idea of why I do think a lot of the TCS community, a lot of the students, and like a lot of the faculty here would find interesting application questions and techniques in these two spaces, in these two threads. But I'll do so by means of two results. I'll highlight the sort of big ideas I have, the big connections, by means of two very specific examples. The first will be about partitioning graphs, like a clean results of how do I divide vertices of a graph in a balanced manner, in an equitable manner. And the second result will be, so the first result will be from fair division. The second result will be from welfare economics, collective welfare, and what that will highlight is that how a principled approach, a very theoretically sound approach, can impact a very important real world problem. So the problem there, which I'll focus on, is called nearest neighbor search, approximate nearest neighbor search, and it is a workhorse. It's a primitive that's used heavily in data science applications. So it's used, for example, in ad display recommendation system. So like Bing, for example, uses it for displaying ads. Spotify uses it for recommendations and so on. So I did a back of the envelope calculation, and I realized that even among the applications I know, it's executed around 100,000 times per second. So now I leave it to you to understand how many times would this primitive run by the time I finish this talk. So it's that scale at which this is done. And what I want to convey to you is that how very nice theoretical ideas impact such an important, improve such an important application. So these are the two results. I will sort of use them to highlight connections. I'll show how these sort of fair division acts like this beautiful banyan tree outside the hall, outside this building, and connects to many other branches in TCS. Before I go to such like the big picture idea, let me just give you trailers, teasers for these two results, so we have something to anchor ourselves with. So what is the first result? Equitably dense subgraphs. Here's the result. So this is joint work with Paratosh. It's quite a clean statement. So what I want to convey to you, and I'll do this in a fair bit of detail, is the following existential guarantee. What it says is that give me any graph G, simple and directed graph, and give me any count K, any integer K. There always exists, I can always in fact find one in efficiently, a partition of the vertex set. So I can look at the vertices, partition them into K parts, such that the edge density of every part is very close. And when I mean very close, I really mean very close. They're additively close to each other within a number 4. So two things, I'm not saying that the ratios are close, I'm actually saying that the density numerically is plus minus 4 of each other, and this is again a universal existential guarantee. For any K, for any graph, I want to convince you that such a partition exists, and edge density is just to recall, is the average number of edges within each subgraph. So here's a picture. So give me any graph, give me any count k. In this example, let's say this is k. What I can do is I can partition the vertex set so that if I look at V1, look at the number of edges within V1 divided by the number of vertices. Look at V2 again, number of vertices divided by 2, yada yada yada. All these densities, so half the average degrees within the subgraphs, they're additively close to each other. They're plus minus 4 of each other. So, and just to pique your interest, this result has nothing to do with graph theory. It's actually not even combinatorial, and in fact, it generalizes to much more beyond graph densities. It's just a placeholder for me to sort of convey a bit more abstract result. But we'll sort of use this as our example. That's polytime. Yeah. Polytime. Always exists, polytime. Yeah. N-cubed algorithm actually. Yeah. Without even sort of much simple dynamic program. Okay, so that's result 1. That's a fair division result because you can think of it as fair division result where I'm partitioning the vertices of a graph among k agents, k entities, and every agent's valuation for what it receives is the edge density. And what I'm saying is I can always partition the vertex set equitably. Every one of these k agents is getting a set that it values within plus minus 4 of each other. Result 1. Result 2 again, as I said, is about neighbor search, nearest neighbor search. It comes from collective welfare. The idea is that how can you use this notion from welfare economics, this welfare function called Nash welfare, to improve diversity in these search results. And as I've already sold on you that this is a primitive, this is a building block that's used heavily in even modern things like RAGs, if you know what that means. It's things that are used to sort of prime large models. Used in recommendation systems, for example, Spotify's NOI is an ANN based system, so on and so forth. So a very sort of a real world impactful application. I'm sort of very happy that Microsoft in fact is testing this out. So it is likely that some of it or ideas from here will actually get deployed. So like a rare feat to have this sort of a end-to-end synergy from like good theory to like real deployment. So that's the second result I want to sort of discuss briefly. These are the two results, and again, this sort of makes little sense right now. What I want to say is like, does it improve? So it improves. So this is not a synthetic data set. This is an experiment we actually performed on Amazon data set. And when you start using the Nash welfare function, you see that you start getting better results. So if one searches for the word shirts, and you're using this Nash idea, you get like a nice diverse set of colors. And if you're searching for blue shirts, you actually only get blue shirts and not like a diversity when it's not required. So this sort of dynamic idea that it lets you find diverse results when required and when not is something that gets executed by it. This picture will make much more sense once I spell out the details, but that's sort of the trailer I have. Okay, so as promised, let me step back now. I will use these examples to substantiate many of the observations I'm making here, but the next few slides are intended sort of for a broad TCS audience. Why should someone like this find fair division interesting? I mean, and my point would be to sort of connect it to many fields and sort of hopefully excite you to look at some of the problems, some of the open conjectures in the space. So the field as such has like really classic history. There's a 7th century Greek epic poem, Theogony, where there is a fair division algorithm, where there's a fair division protocol. In fact, there's a biblical reference to that. It's called the story of Abraham and Lot. You have a piece of land, you have to fairly divide it among two individuals, Abraham and Lot. And here's the algorithm. It's the so-called cut and choose protocol. Abraham looks at the land, divides it into two parts that he is indifferent between. So the large piece of land, here's a cut mark. Abraham is happy either with the left part or the right part, and then Lot comes in, picks among the two that he likes more. So it's an envy-free protocol, and this is a story from the Bible. There you go. That's sort of the genesis, if you will, of fair division. The mathematical study started in the 1940s, so even that has a rich history. The classic literature deals with problems like cake division. So cake represents divisible resources, things like land, water. And there's a lot of work in terms of market equilibria, and a very distinguishing feature of this work, which I think TCS should get inspired by, is axiomatic study. So we will see this again by means of the example I promised, but what math econs did, which sort of something to get sort of take note of, is the fact that a lot of their objectives are axiomatically supported. So they do not just pick a maximization objective, or let's say a minimization one. They actually start with axiom. They say, I want a function that should satisfy these properties. This could be like fairness properties, economic efficiency properties, and so on. And based on these axioms, then they sort of identify the right objective to work with. And what we'll talk about, Nash welfare, is one such objective. So this study of axioms, again, quite classic, but it's something that we should learn from. Of course, elements of mechanism design, so truthful, strategic, participants, and fair division, like bread and butter of a lot of economics. The modern themes are, like, again, interestingly, are combinatorial. So this is like a big, like a lot of activity around this in recent days, certainly by computer scientists, and the focus a lot on, in contrast to classic results, is on combinatorial things. So for example, instead of dividing things that can be fractionally assigned, like water, land, a lot of new results focus on discrete division, like allocation of houses, kidney matching, or course allocation, and so on, or partitioning vertices, things that you cannot fractionally divide. A lot of work in discrete, of course, algorithms, complexity, so on and so forth. So a lot of new themes, a lot of classical themes, so it's a rich space. And this is something that I really sort of promised you earlier, like connections, like why should a general audience enjoy or take interest in this? And it has many. I already gave you a graph partitioning results, that will be sort of the focus of a large part of this talk, but even coloring problems, like the classic Hohenal-Semeredi theorem, which says that not only can I color a graph with, let's say, maximum degree plus 1 colors, in fact, I can color any graph with maximum degree delta, such that with delta plus 1 colors, such that every color class is balanced. They have the same number of vertices, so on. So this, you can think of it as a fair division, as a constrained fair division. You have chores, you connect chores that conflict, you partition them among delta plus 1 agents, so that every agent gets the same number of chores without any conflict. That's Hohenal-Semeredi. Looked from my perspective, that's a fair division result. So we have ongoing work with Vignesh, with like look at, let's say, weighted versions or other notions thereof. So coloring, graph partitioning, certainly a lot of connections to fair division. Even matroids, constrained fair division, you can think of it as like assigning independent sets of matroids to agents, captures things like house allocation and such. And there are recently nice results, like one that studies the so-called one equitability result in matroids, or even classic conjectures in matroid theory, like White's conjecture, have direct implications and connections with result, like certain fairness guarantees. Extremal combinatorics, again, extensively studied, but has found connections and implications within fair division. There's this nice result that shows that this Erdos matching conjecture actually connects with what is called quantile shares, a notion of fairness. And also there's this very prominent fairness criteria called EFX, which connects to rainbow cycle. I'm not giving you a lot of details. My purpose is to sort of like just have a slide with some names. Someone can take a picture and sort of look at it if you want to. Discrepancy theory, again, you can, now that I've said it out loud, you can just think of it as a fair division problem. Like vector balancing is a balancing problem. You're partitioning vectors such that like sum of vectors in one part, component wise, is close to the sum of vectors in other part. And so it is a fair division problem. And to quote Kabir, Chit Dekhun Tit Lal, so the last one is more my like biased perspective. It's not really how many people would say it, but like to me, even Caddis and Singer or Weaver's conjecture is a fair division problem. You are given a matrix, you want to partition the vectors such that the spectral norms are close to each other. You might call it Caddis and Singer celebrated, but for me, it is a fair division where the valuations happen to be the spectral norm. So again, I'm wearing red color glasses, so the world does look red. And this is again a partial list. It kind of goes on. Again, most standard TCS, many applications, many connections. What I do want to say is that while it does connect very well, in terms of hammers, it actually is distinct. So, for example, the consensus result actually is proved using topology. It's using a result from topology, the Boucher-Coulomb theorem, whereas discrepancy uses a lot of combinatorics like the Spencer's pigeonhole idea or SDPs or these Comlosh style convex optimization techniques. So it does bring in a new set of hammers, and it's worth considering. We will in fact look at an application of Sperner's lemma, but there are many like fixed point theorems, this KKM theorem, so on and so forth. These are results from topology, and they do have applications in fair division, both the divisible classic settings and now in these new combinatorial discrete settings. So lots of new hammers worth trying off. Another technique that I do want to really highlight is like something that gets flipped, is that there are results in fair division that use markets for algorithm design. So let me say this again. So unlike the well-established algorithmic game theory paradigm where you develop algorithms in the service of economics, so you develop algorithms to find equilibria, there are now results which say that, oh, you can take a market, results from market equilibria, use that as a technique to design approximation algorithm. So there's this constant factor approximation known for Nash welfare. It actually does follow this template. So it uses the concept of Fisher market to develop an algorithm. So sort of a reverse brain drain, if you will. And of course, standard theoretical computer science, probabilistic methods, approximation algorithms, you name it, it does appear a lot in this literature. So lots of interesting techniques, lots of interesting connections, and what really sort of excites me about it, is it's a very fertile ground. There are open problems, like there are deers on this campus. It's everywhere. There's something called the EFX conjecture. To the students, look it up. It's a very pithy statement. You can explain it to your younger cousin who's giving boards, and do lose some sleep over it. It's that beautiful problem. It's a very succinct, very nice problem. If you don't like someone in your hostel, tell him to prove it, and that'll be a remedy. There are many other sort of interesting questions, and talk about gaps, right? So there's this cake division problem, division of like a fractional resource, a resource that can be fractionally assigned, and there's a huge gap. The best no lower bound is something like n square, and the only known algorithm for it runs in that time. Yes, it's a tower of 6 n's. So if n is 4, you have 4 agents. That's going to take more than the lifetime of the universe to run. Nonetheless, it's a finite time algorithm, and the lower bound and the upper bound are by no means close to each other. So large gap, good open problems. I could have given a 1-hour talk on just the open problems on it. They're nice surveys. Again, I do invite you, the students, to take a look and sort of go through it. So with that, that's the big picture landscape. The many things I mentioned are sort of quick with my time, but what I do want to do is focus on these two results and sort of convey some of these observations a bit more precisely. So let's start with the fair division results, and then after that, however much time I have, I'll focus on the collective welfare part. So equitably dense subgraphs. This was the statement I told you. Any graph, any count k, I can always find a partition. So give me a social network, however large, 1 million people in the social network. Give me any group count k. I can always find k groups such that the average number of friends within each group is plus minus 4 of each other. Additive bound, and again polytime. I can find it. There's an efficient algorithm as well. Do notice, just to make a few remarks, I'm not looking at an optimization problem. I'm not telling you that the densities are going to be large or small. All I'm saying is that the k parts will have densities close to each other. So it's really a balancing problem and not an optimization one. Yes. It does. It's just looking at one part and whatever the density there is. Yeah. No, good question. It's open question. Not yet. So what I can tell you, and you'll actually, I'll repeat it since you have asked. If you give me a Hamiltonian graph, then I can guarantee that each VI is connected, but not in general. Yeah. Okay. So that's the edge density. Again, Saturday evening, let me give you examples. So here's a graph. It has 13 plus 3 vertices, a complete graph on 13 vertices, a complete graph on 3 vertices. Number of edges is 13 choose 2, that's 78, plus 1 plus 3, 82 edges. And let's say I pick k as 2. So I want to partition it 2 parts, so that the edge density of the paths are close to each other. This is not a good attempt. So if I take these 3 vertices as V1, all these orange vertices as V2, the edge densities, if you do the calculation, are more than 4 away. But I could be slightly smart, take these 10 vertices, so 7 plus 3 as V1, take these 6 vertices as V2, and the edge densities are again exactly the same. So here it happens to be connected, but in general, like the question that she has asked was, can you guarantee that each V1 and Vk are connected? In fact, balancedness is also an additionally nice thing which we don't have an answer to. So that's the result in more generality. Let me just drop the mic and not create suspense. As I said, the result has nothing to do with graph theory. It's not even combinatorial, strictly speaking. It comes from cake division. Like, nice to hear cakes on a Saturday evening. Here it is. And yes, it's not. There's a recent work by Hussaini, Vishwaprakash, Sethia, and Yadav that improves it to 1, and 1 is sharp. The proof has nothing to do with graph theory. The result, of course, yeah. Yeah, I mean, even on a Saturday, I shouldn't have made this mistake. Yeah, the proof is not graph theoretic. It's for the equitability, they get it to 1. This thing, instead of 4, it's 1, and 1 is right. Okay, cake division of a divisible resource, classic stuff for this literature. So what is a cake? It's represented, it models this interval 0, 1, right? So it's a divisible heterogeneous resource. Divisible in the sense that if I have n agents, I can give every agent an interval within 0, 1. So like a piece of the cake, an interval 0, 1. And heterogeneous because the agents will have different values over different parts, different intervals of the cake. So here's a quick illustration. 0, 1, that's my cake. Take any interval, take any agent A among the n1s. I have a value function associated with the agent. So it has some value, let's say non-negative value Va for this interval I. And similarly, if you give this agent a different interval j, it will have a different value again, Va of j. So Va is a function that maps intervals, baby intervals within 0, 1 to non-negative numbers. That's the valuation I'm going to look at. I have n agents, I have one value for all of them. So what I want to do, what is the cake division problem, is that I have n agents, they have these valuation functions that map intervals of 0, 1, 2 non-negative numbers, and I want to find n intervals in the cake. That is, want to look at 0, 1, make n minus 1 cuts, and hence I get n intervals, then assign them, permute them among the agents such that it's fair with respect to these heterogeneous valuations. And a standard notion here is that of NV freeness. So what I said again, let me repeat. What I want to do is look at this cake and I make some n minus 1 cuts. So I get, let's say, an interval IA. I give it to agent A. I get another interval, the second one from the left. I give it to agent B and so on. So partitioning the cake means making these n minus 1 cuts, and the resulting intervals are assigned, permutate among the n agents. And the requirement, the classic quintessential notion of fairness in this field is called NV freeness, and what it says is that you divide the cake and then assign the intervals such that no agent envies anyone else, i.e. every agent A looks at the interval it has received, so looks at the value it's gaining from the interval assigned to it, and that value has to be at least A's value for any other interval IB. So do note, both sides of this inequality are evaluated with respect to I's valuation, the valuation that maps intervals of 0, 1, 2 non-negative numbers. It says that I is happy, satisfied with the interval assigned to it, and at least as much as any other interval. So the right hand side is IV left, and this inequality should hold for all pairs of agents A and B. So every agent is NB free, looks at a piece of the cake and says I don't want it.
So these n intervals are given to you, right?
No.
So how is this partition function specified?
Let's, for the time being, be mathematicians and just say it's a function. Yeah, it's usually done through what is called the Robertson Web query model, but I'm only going to tell you like a existential guarantee. So there is a function VA, that's a well-defined function. I'm not looking at a computational problem as of now. Yeah, just an existential guarantee. Does that? Okay, great. So just to repeat, the intervals are not given to me. The point is to make these cuts, find the intervals and assign them such that this NB freeness holds for every pair. Okay, very well studied. Like these are books from even the 80s. They're like 4 more. I just ran out of space on the slide. So, I mean, a lot of literature around it, a lot of good math, very interesting applications like border dispute resolution and so on. So, rich literature, rich in terms of application, so well-studied theme. And again, interest of time, a lot like raise suspense. Here's the punchline. Beautiful result by Su. And what it says is that this might look very surprising to you, but such a division always exists under very mild conditions on the valuations. In fact, you give me a valuation function that's non-negative, continuous, and it satisfies what is called the Hungry condition. I'll spell out this condition in a minute. Very mild 3 conditions, and such an NV-free division is guaranteed to exist. Do notice, all I'm assuming is non-negativity, continuity of the VAs as a function of intervals, and this Hungry condition, which I'll spell out in the next slide. But in particular, VAs do not have to be monotone. They do not even have to be additive. So I'm not saying that value of 2 intervals that are right next to each other is the sum of the values of the individual intervals. Any valuation that satisfies this, such a division always exists. Give me such valuations, there always exist n-1 cuts and the reallocation of the intervals such that every agent is NB free. And the proof is literally by that picture. It's called Sperner's lemma. I'm very short on time, but yeah, there are beautiful YouTube videos on it. Again, next time if you're watching a reel, stop yourself and watch this proof. Yeah, you'll thank me. But this theorem statement is here, but very nice, super elegant proof that can be explained really in a very nice video. So the Sperner's lemma with some labeling ideas really give me Su's like universal existential guarantee. That give me a cake, give me any number of agents n, give me these values, valuation functions, the continuous, Hungry, and non-negative, such a thing is guaranteed to exist. Okay, what is the Hungry condition? Let me sort of not delay it further. All it says is that if you give me any partition of the cake, it will value some interval over the empty one. So let's say that you value the empty interval at 0, you make n-1 cuts, you have n intervals now. Some intervals can in fact be empty. You can make 2 cuts at the same point, but there will be a non-empty piece that the agent values at least has a positive value for it. So the agent is hungry. There's some part of the cake she'll like than any other piece. So that's the technical condition, and you actually, it really pops out of Sperner's lemma. If you see the proof, you'll see why it makes natural sense. But that's the Hungry condition. Let me repeat myself. I do not require monotonicity of the VAs. I certainly don't want additivity or any other structure from the VAs. Any continuous function that satisfies this condition, the Hungry condition, Su's lemma is applicable. Yeah. Yes. They are all valued at 0. That's the term valuation, like implicit. Yeah, it's a condition. Let's say, yeah. And they are indistinguishable. Yes, yeah. That's Sue. I started with a graph and I've ended at the cake. Good journey. But if you think that's sort of too simple, let me sort of temper our ego a little. There's a nice result by Stormquist, and this addresses the question that was asked, like how is this given? So even if it's given in a very natural query model, forget polytime, there's no finite time algorithm for it. So I can give you, like, for example, rational valuations at rational at all rational, and you'll never be able to find it, like sort of an adversarial Stormquist thing. So this result holds if I'm forcing this condition that I'm making n minus 1 cuts. There's a more relaxed model where you make many cuts and then give unions of intervals to agents. And this very complicated algorithm, Aziz and McKenzie, works in that relaxed thing, but that's the running time. Improve it, and I'll like you more. Unconditionally. It's not a hardness result. There's no finite time algorithm for it. It's actually like an irrationality. It's like I can make sure it's at a point where you keep answering and I keep moving so that you, for infinite, like you keep having smaller and smaller but positive NV. I mean, if you think convergence, closeness and open set arguments was an unnecessary course in your undergrad, read these proofs and you realize like why closeness really matters. This is actually, no finiteness rests on the fact that if you can I can infinitely make you walk smaller and smaller steps in an open set. So again, very interesting stuff. You regained appreciation and respect for topological concepts. These were algorithmic things, but the existential result stands. And this is where I want to get to. That's my end goal, the graph partitioning. And I am actually going to give you pretty much the entire proof. I'm going to start from there and establish this graph theoretic result, and in fact address a few of the questions that were raised like during the conversation. Okay, so how do I do this? Here's the idea. Light bulb is here. I have this graph, I have this integer k. What I'll do is I'll look at my cake, 0, 1, and let's say I have capital N vertices. That's the number of vertices I have in the graph. What I'll do is partition my cake into these baby intervals, each of length 1 over capital N. So I have exactly capital N contiguous intervals, and I'm going to associate every vertex of the graph with one of these intervals. Doesn't matter in what way. So let's say the vertices are indexed 1 through capital N. Just associate the first baby interval with vertex 1, the second baby interval from, oops, shouldn't have done that. It went out of the full screen mode.
That's okay, I got it.
Thank you. So, yeah, the first interval with the first vertex, the second baby interval with the second vertex, and so on. So I have capital N of these small baby intervals, each of equal length, and I just associate all the capital N vertex one with each. So what do I have? I have the density function defined for me. What I'll do is I'll use that to define a valuation over the cake. So I have this rho function that I'm inheriting from the input graph. From that, now I'll define a function over this cake, in fact over intervals of this cake. So let's do that. So take any interval. Let's say it starts at this baby interval between s minus 1 by capital N and s by capital N. So that's the baby interval associated with the sth vertex, and it ends at the interval associated with the tth vertex. So it's completely covering, integrally covering the baby intervals of vertices s plus 1, s plus 2 to t minus 1, and it's partially covering the intervals for s and t. I'll just do a linear interpolation of the density function. That is, the value I have, I'll define this function for any interval as the following. So it looks complicated, but just follow me along. All I'm saying is that the vertices whose intervals are completely contained, I'll take them integrally, and the ones that are fractionally contained, I'll take them, let's say, with probability proportional to however much the overlap is. So if this R is this random set where vertices s plus 1 to t minus 1 are always there, vertices s and t are included with some probability proportional to how much the interval is being covered. Whatever the expected value of the density function is, that's my f. This is called a multilinear extension of a set function. There's some technical reasons for this particular choice, but for the purposes of the talk, all you can think of is that I started with a density function defined over subsets of the graph. So in particular, it is defined for contiguously indexed vertex subsets. I can use that to define fi. Just linearly interpolate it. The interpolation ensures that this gentleman right here, f is continuous. Yeah, I mean, what I just said kind of holds true. It's just an extension. So in particular, if I look at an interval that starts at an integer multiple of 1 over capital N and ends at an integer multiple of 1 over capital N, the f value for that interval will be exactly equal to the rho value of the vertices that are completely covered. So if x was in fact s minus 1 by n and y was t by n, f, the function of the interval, would be exactly rho, the edge density of vertices s, s plus 1, s plus 2 and so on. So Shreyas had asked a function about continuity. So what I'm saying, what you could have done was taken a Hamiltonian path and indexed him in such a way, but I'll get to it in 1 second. But that's the function I have defined over a cake. So I started with a set function rho, the edge density function. I've landed at a function f that's defined for every interval of this cake this way. Okay, continuous function, it's non-negative because rho is non-negative. Can I apply SU? No, it's still not hungry. Right, so you could have looked at a partition where the edge densities are all 0, so it's not a hungry condition. I hate to admit it, but this took actually a few days to figure out. Here's the fix. You just pick an arbitrary small epsilon and add the length function to it. So you have this function f, and now you add a function length of I, which is positive for every interval of like every positive length interval, very small epsilon. Just add it and you have this new function v, and this is the valuation function I have. So I started with a cake. I had this count number k. I started with a graph with a count k. I've now constructed a cake, and what I can do is consider k agents, all of whom have the identical valuation v. They have the same value function. So it's a special case of SU, in fact, where all the agents end up having the same value function. And this sort of distinction really helps me get a polytime and beat the impossibility result I mentioned earlier. So I'm going to invoke SU. In fact, I'm going to invoke it with k agents, all of whom have the same valuation function v. Okay. Yes. 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 It will be 0. Yes. Yeah. Okay. X and Y are in the same thing. Then whatever the length, let's say they cover 1 over 2n. So you'll include this. So right now I'm only defining v. What you are talking about is like a rounding error. Right. So if both of them are in the same baby interval, you will still include it with some non-zero probability. For right now, it's just a definition of v. It doesn't have to be like sort of consistent across like contiguous intervals. Okay. It's a very subtle point. I am going to punt on it, right? Like the fact, but what you are saying is actually going to matter. This is the advantage of giving talks versus writing papers. I can skip details I don't care for. But just to answer this question, like if they are very close, what you can assume is that n is like k is less than n by 2. If it's n by 2, you can just take pairs of vertices and get the edge density 1 or 0. And if it's n by 2, you can argue that all of them will have sufficient length. So the end I star, which is about to show up, you'll never be in this case. You can sort of do some pre-processing for that. So, okay, I have this valuation. I apply SU with k agents that have the exact same valuation function defined on the cakes. And what SU guarantees me is this existence of this magical partition I1 through Ik star. Since the valuations are identical, the allocation doesn't matter. I can give any interval to any of these k identically valued agents. And what do I get? I get that the values of all these intervals under this function V are the same. Let me just summarize. I had my density function rho. I got extended it to find a function on intervals of the graph, intervals of the cake. I changed it a little bit to get the Hungry condition, and under this V I have this NV free allocation guaranteed to exist, which satisfies, I am scared of doing this, but satisfies this thing that every agent is NV free and they have the same valuation. So value of all the intervals under V is exactly the same. So every agent is indifferent, the k agents are indifferent among the k intervals. Great. I'm home actually, not literally, but at least in the proof. So what this V means is that, so this equality, I can just spell out what V is. It's F plus epsilon length, so I have this equality. Note that length, the cake itself is 0, 1. The length cannot be more than 1. So there's an epsilon additive term. Great, but what do I get? I get that even with respect to the extension I had defined for the density, up to epsilon, I am very close. Okay, great. F is the proxy for the rho function defined over the cake, and all I have to now do is, as Professor Jayakumar was pointing out, round. I have intervals which really, if it's starting and ending at an integer multiple of 1 over capital N, it actually does exactly corresponds to a vertex subset, but you could have some like that line in between, not a big issue at all. So if it starts here and ends here, what you do, here's a simple thing, you just shift it to the left. So if I star was for agent I, you give Vi, define Vi star, you just start at S and end at T minus 1. Just literally round it, shift it to the left, and you will get from these k intervals, you will get k subsets, V1 star, V2 star, Vk star. Notice that not only am I giving you V1 star, V2 star, Vk star, I am telling you that they actually are indexed exactly in the right order. V1 star will have vertices 1, 2, 3 up to some number. V2 star will start at the next vertex and again stop somewhere, and yada yada yada. So if this was a Hamiltonian path, just to answer your question, this would be connected parts of the path. Okay, that's V star, and the final thing that's left, again, this is property that I got because I was careful in defining my extension, that this function and this function, this apply to intervals and this apply to the rounded subsets, are only going to be 2 away. So just plug it in. I mean, you have the top thing, you can drive epsilon to 0, and this is what you get. This 2 is why you get a factor 4. You can improve it, as I mentioned. Recent work by a bunch of co-authors, in AMAS, I think. Okay, that's the result. That's the proof. Cakes lead to graph partition. Yes. You can carry out with any epsilon. Yeah. Not any epsilon small enough, sufficiently. You can argue that the density function, right, will take some sort of rational value. So pick an epsilon that's small enough that if the inequality holds with epsilon, it has to hold without epsilon. Sufficiently polynomially small epsilon works. Yeah. Does that answer your question? Yes, it does. But small enough, like 1 over poly in capital N will suffice. Yes. I will give you a stupendously generous result in 2. I've actually fooled you into thinking it's a graph theoretical result. I never used the fact that it was a density function. I could have done with any discrete set function. I've actually given you the proof for the generals. I just use the graph as a sort of toy in some sense. Like, so 2 slides and I'll answer your question. But you've actually seen the general proof. So notice just to repeat the question, I've never used the property that the row I started with was the density function. The only thing was that rho and f are additively close. That's like a Lipschitz property of the set function. So I'll give you a general statement and we can sort of discuss this one more time. So there's a polytime algorithm, and just to speak on that, it has nothing to do with density function. Here's another invocation. Instead of rho, you start with the cut function of a graph. And the result now says, give me any graph. Let's say it has maximum degree capital delta. I can always partition it among any k vertex subsets such that the cut functions are almost 4 delta each other. The 5 comes because I do want non-emptiness property, a technicality that I'll skip today. But what it's saying is that, okay, look at this graph, these red vertices, they have like 1, 2, 3, 4, 5 edges going out. Look at the blue ones, they have 4 edges coming out. So you have these parts, and you count, if you look at the number of edges that are going out, they are very close. They're just 5 times the maximum degree. Here's the general result. In fact, I have proved this to you. I just sort of didn't tell you I'm proving this. Give me any set function, f. So it's a set function. So it's defined over subsets of a ground set capital V. The only property I want is that it's non-negative. Again, only property I want that is it's non-negative. It can be non-monotone, doesn't have to be submodular, subadditive, nothing. Any set function under God's green earth, as long as it's non-negative, for any k, I can find, not find, but again, oracle question, there exists a k partition of the ground set, so the function values are additively within 4 of each other with the scale factor, the Lipschitz constant of f. So Lipschitz of f is just that how much does the function fluctuate if I add or remove one element. If that is small, which happened to be 1 for the density function, happened to be maximum degree for the cut function, this is it. So yeah, as I said, like very general things, and I hope to find other applications of this. Okay, I'm done. I have like roughly 10 minutes left. I will like quickly go over the other thing. If you have questions, I'm happy to answer. I'll switch gears and talk about a bit more applied work on this welfare functions. Excellent. So Nash welfare, Nash social welfare for neighbor search. So this result has 2 parts, and my only point is to tell you the pillars. Once they are there, the arch, you can sort of make it for yourself. But at the same time, here's the big picture that I really want to convey through this part. And this is more like why is this sort of direction interesting? Why is this program interesting? And the idea I want to convey, modulo all the technical details and the specificities of the result, is that it is very interesting to now look at algorithms as economic policies. There's a lot of talk about using AI ML tools for socially sensitive decision making. Things like algorithms are deciding on whether loan applications get resolved, admission policies, things like filtering CVs. So there are a lot of algorithms that are really impacting people at large. They are impacting the same way as economic policies do, the same way as like tax policies or tariff policies impact a large population. Algorithms are in the same realm now. Also, like economic policies, these are not very engineered constructs anymore, especially with very large AI models. They are learned from data. They have lots of black box components, so they're not extremely engineered, like hard-coded steps. So even then, like this sort of synergy or the sort of similarity between economic policies and algorithms show up. So the big idea I have, the thesis that I'm sort of posing in front of you, is that the same way as, let's say, World Bank looks at an economic policy, looks at how decisions will impact populations at large, we should look at such algorithms, especially when they're making socially sensitive or responsible decisions, as like as economic policies. And this is not just sort of a meta statement. The example I'll tell you is a very concrete instantiation thereof. I'm going to look at a primitive, this nearest neighbor search, and kind of actually use a very specific construct from welfare economics to sort of quantify that. And in all of these applications, and the one that I'm about to show is one exemplar, but the point is that the algorithms decisions, and when I say algorithms, I also mean like AI models or machine learning tools, they do induce utilities or rewards. And be imaginative. When I say rewards and utilities, it's not necessarily monetary, though it can be. Like if an algorithm is deciding on a loan application, the reward is monetary. But algorithms can also decide like course allocation, which then can impact your CGPA, or like they can filter CVs, in which case the reward is the opportunity you get to say interview at a place, so on and so forth. So these are like very general terms, and what economists have done, what welfare economics has done wonderfully well, and this goes back to this axiomatic treatment I was talking about, is that they have come up with welfare functions that do satisfy some very nice properties. Let me reiterate that point. It's sort of important to keep at a high level message. The point is that here I'm not starting out with an objective function, right? Instead I'm saying, look, I have to evaluate valuation. So I can make decision 1 and it will result in some values among a population, let's say of capital T people, or I could make a decision 2 which will result in a different tuple of valuations. So how do I compare these two? Right, and the way to compare is that you come up with a function that composes these t numbers into a single number, and then say whichever is higher, that's a better distribution. But what I'm not doing is that saying, okay, here's a good way to compose, let's apply that. What ends up happening is that you list out properties that you want of such a function, and then in fact you can filter out and say that, oh, this is the right function. It in many cases is the unique one that satisfies these axioms. Okay, just a simple example, slightly late, but imagine that you have a policy decision, or let's say an allocation decision, and you're running it among 4 people. So you can decide on some taxation policy which results in these utilities for the 4. The first person really benefits, gets 100, the rest 3 get a utility of 0. Or you can decide policy 2, in which case this is the realized 4 values, the utilities V1 through Vt of the 4 t equal to 4 agents, so on and so forth. What valuation functions do is like they give you a function that maps these t tuples into a single number. The higher the value, the better it is. And here you can actually see what if you want to be fair or like take care of the collective, and these are better metrics. But at the same time, do note, if I were looking at the sum, which is like a very ad hoc choice, the sum of the utilities, you would have gone here. The sum here is the larger than the other two. All I want to point out is many a times, including when your CGPA is being calculated, you are using the sum. You're using the arithmetic mean. It's not always the best metric of choice, especially in sort of the socially sensitive or decision-making context. Here, the minimum person is as happy as possible, so more like an egalitarian choice. The last two maximize what is called geometric mean. And this is what I was trying to say. I mean, I'll not have time to go into what these axioms are, but the way we land up at the Nash welfare function is like by studying these axioms. So we start at these axioms and realize that there's only one function that actually satisfies all of them, that happens to be the geometric mean of the utility. So you look at values, and which is a better tuple is defined as the tuple that has the higher geometric mean. So again, this was something we discussed, like this is maximized at this vector, the right hand side here, but this achieves a balance between complete fairness, the egalitarian extreme, and the utilitarian extreme of looking at the sum. Say that again, please. Yeah, so I'll add like a smoothing constant to take care of that, yeah. So we shift it a little to, it's a technically important thing, but I'm not, purpose of the talk, I'm sort of skipping that. Okay, so that's the geometric mean. So I told you this problem has 2 pillars, one coming from welfare economics, Nash welfare, done. The second actually coming more from computer science, a very, very prominent problem, the nearest neighbor search. I'll finish in 5 minutes. Yeah, it's called the nearest neighbor search, but again, sort of extremely nice even from a theoretical standpoint. And the problem as such is quite simple if I had linear time to solve it. So what's the problem? I'm given this list input vectors p1 through pn, they're d-dimensional vectors, and at real time I'm given a query q, again a d-dimensional vector, and some small number k, and all I have to do is find the k nearest, the k most similar vectors among p1 through pn. So if I could scan this entire list, very easy problem. With order n time or order n times the dimension time, it's very easy. The catch here is that this actually, as I said, it's back of the envelope tells me it's roughly 80,000 times per second, and that's only the applications I know of. So even before I finish this sentence, this thing would have been executed more than 80,000 times. So you have to do it at large scale. In many applications, n is actually web scale. A billion vectors is not a rare thing, and D also is large. Like the dimensionality of these vector embeddings, as they are called in many applications, tends to be like thousands or more. So you really have to come up with a data structure over the input vectors, so that if I give you a query, you can really solve it with very astonishingly low latency. So yeah, again, formally it's a clean problem to state. I just want a size k subset from the input set, so that this total similarity is maximized. You get the k most similar vectors. Approximate means that, okay, exact you can't do better than order n, but I allow you some approximation in this objective, that's a and n. And they're products, like really large scale products, like disk ANN is the one that Microsoft uses, Annoy is Spotify, Gemini has its own, I'm forgetting the name, but yeah, there are dedicated clustering based or graph based data structures for solving this problem. Okay, what is the objective that I'm now going to address? The point is that it works wonderfully well, but what ends up happening in a lot of these applications is not only do you want k most similar vectors, you do want some diversity among the k most vectors. So for example, if you look at the product examples, Amazon has a catalog where all the products are expressed, so-called embedded as vectors. The query now is a keyword query. A user comes in, searches for the word shirts. That word shirts is again mapped to a d-dimensional vector q, and they really do vector like nearest neighbor search to find for this query q shirts k products that are closest to it. So that's how catalog search in many cases works. So when you do return shirts, you actually not only want the closest ones, but do want some diversity among it, say in terms of color or certain other attributes. So this is a problem that really is was an issue for many of the products. It's coming from the real world. And again, unlike many cases where things like diversity and responsible AI is not well defined, here it's rather cleanly set up for us. You have attributes. So every vector among those capital N has some subset of attributes, and you want diversity with respect to these attributes. Okay, and this was a solution that was deployed in many, many cases. It's again still deployed in some real world applications. What you can do is simply put a hard constraint. Say that, look, I want to maximize this objective, the same objective as before, but no attribute should appear many, many times. So you pick this ad hoc number k prime and say that return the vectors that are closest, but no attribute should dominate the set of k things you have. So any attribute should appear at most k prime times out of the k times that you have listed. So here's the issue with it. So if I search for shirts, and let's say I constrained it that white or black cannot show up more than 3 times, great, I do get diversity now. I have 4. With a hard constraints, I've limited the number of black shirts, let's say, to be 3. But the catch in this was actually observed by product engineers. If you now instead search for the query word blue shirts, so you have the same set of vectors p1 through pn, q, instead of being the vector representation of the word shirts, is now the vector embedding of the word blue shirts. A hard constraint is a bad thing. when the query is blue shirts, you really do want all 9 shirts or all k shirts to be, k returned vectors to have that attribute, to have blue. So that was one concern. The other concern is, if you just think about it a minute, this actually independent set hard. It's a fairly nasty problem even to approximate, and heuristics like really were struggling at it. So here's the key insight, the magic moment, right on time. The idea is to look at these attributes as agents. So literally think of them as entities, and the choice you make, the k vectors you make, actually attribute utility to them. So here's the setup. You look at every vector that you select, every k vector. Now for every attribute L, if this vector has this attribute, so you pick a shirt, and if it happens to be red, then you increase the utility of the red color. So if you have 20 colors in your entire catalog, you have 20 agents, and for every color, what you can do is compute this utility for any subset of vertices, k vertices that you pick. So it now maps it to a welfare setting, and you can maximize the geometric mean of these utilities. Just to address this question of 0, you can add this offset of eta to make things non-zero. And again, this was where I started. If you do this, again, this is real, it's not synthetic, this is Amazon data set. We have many more plots, but out of respect to the center, I did not include them. I really have system looking plots. But if you use this objective, you can kind of see that when you do need diversity, it gives you diversity. When you don't need, it organically sort of manages to do well. The theory result is that unlike the constrained one, which was independent set hard, this does have a 9 approximation. They're good heuristics, something that we actually have deployed. In a few weeks, we'll make the code even on GitHub. So I will stop there. Thank you for staying back on a Saturday.
For the graph theoretical results, have you looked for graph theoretical proofs of the same?
So the improvement to 1 is like quite combinatorial. It's like a local search thing. The point which I didn't sort of allude to is that this sort of machinery does give me guarantees for NV freeness as well. So even if you had like heterogeneous valuations, you do get nice results. So for that, we haven't.
Okay.
Yeah.
Got it. Because you mentioned this Hamiltonian path thing where you actually get these connected.
Yes.
But that implies that there is a stronger version, right? That for any ordering of the vertices,
yes,
you can.
Yes.
Yeah.
So this gives you a counting result as well.
Right.
So then not only 1, but you can use that idea to say there. In fact, notably many of them.
Right.
Yeah. But I mean, the improvement by Hosseini et al. Is combinatorial. But this technique of mapping it to a cake lets us do, like, this was one result among many. It lets us like get something like, for NV freeness as well, it lets us establish results. Yeah.
Okay, thanks. And since you mentioned cake so many times, do you also have cake for us?
Yeah. We'll go to one of the bakeries, Nisha. Yeah.
Any other question?
Yeah.
Yes. Siddharth?
Yes.
Okay, so what was special about using Nash social welfare for the neighborhood search? Any other objective function or the axiomatic properties of Nash social welfare make it a uniquely good choice?
Not really. Like, so if you force scale freeness, and this was probably something that I sort of, the only function you can pick is Nash welfare. Yeah. So it's a function that wherein my hand is forced. So if I want scale freeness and these other axioms, up to sort of these eta shifts, that's the only thing I could have picked.
And do you have any thoughts, like if we can relax any of this, does that open up the possibilities of looking at?
So you can, I mean, you don't have to have scale freeness, but then you can look at egalitarian welfare. And like, there's a generalized version called p-mean welfare, so the entire family of functions you can look at. Yeah.
Thank you.
All right, so in the can you take it offline maybe? Yeah, so in the interest of time, let's thank our last speaker. And let's present a token of our appreciation.
Yeah, let's also thank all the organizers for this wonderful event.